Welcome to The Explainer. I'm absolutely thrilled you're here today because we're going on a wild journey, and I mean a literal, immersive descent straight down into the single most unexplored domain on planet Earth. We map the stars, we send rovers to Mars, yet the vast majority of our very own ocean floor remains a total mystery to us. So today, we're going to dive into the sheer physical engineering it takes for humans to just survive down there, and the unbelievable biological engineering that deep-sea creatures use to thrive in absolute freezing darkness. Okay, let's jump right in. I want you to really think about this for a second. What actually happens when you leave the sun completely behind? Imagine stripping away all natural light, all the warmth we just completely take for granted up here on the surface. What kinds of incredible adaptations and what kinds of radical human technologies are required to survive in an environment that literally wants to crush you? The answers sound like pure science fiction, but they are happening right now, deep below the waves. Section 1. Into the abyss. To really understand this descent, we need a mental map of where we're going. The ocean is basically layered. The upper 200 meters is the sunlight or euphotic zone. That's where you've got abundant light and most of our commercial fishing. But as we sink lower, between 200 and 1,000 meters, we hit the twilight or dysphotic zone. The light drops off so incredibly fast here that photosynthesis actually becomes impossible. And then, once you cross that 1,000-meter threshold, you are officially in the midnight or aphothic zone. Down there, it is a world of absolute, crushing, uninterrupted darkness. Section 2. Engineering the deep. So how on earth do we even get down there to see anything? It requires a monumental level of human ingenuity. Back in 1930, William Beebe and Otis Barton managed to reach 435 meters. And the way they did it is wild. They essentially dangled themselves on a single cable inside a tiny spherical steel pressure chamber called a bathysphere. They were literally just peering out of a little window to look at jellyfish. If that one cable snapped, that was it. It was incredibly brave. By 1960, Jacques Piccard and Don Walsh took the Trieste down. And then, in 2012, filmmaker James Cameron made his famous solo dive in the Deep-Sea Challenger. And we really need to emphasize the sheer scale of that 1960 Trieste dive. They descended an astounding 10,915 meters into the Challenger Deep in the Mariana Trench. Down at that depth, the hydrostatic pressure is almost unimaginable. We're talking thousands of pounds of pressure per square inch trying to crush you from every single conceivable direction. So the obvious question is, how do you survive the crush? Deep-sea explorers rely on brilliantly constructed pressure-resistant chambers. Engineers use spherical geometries because a sphere is literally the best possible shape to evenly distribute all that lethal stress, minimizing any chance of buckling. They build these out of ultra-strong materials like high-yield wrought titanium or steel, and then they use specially formulated lightweight synthetic foams. This whole system works together to protect the humans and the delicate electronics from freezing temperatures and unimaginable pressure. Section 3. The ocean's twilight zone. All right, so our engineering is intact and we are safely passing down. But as we drop past that 200-meter mark, the warmth just fades away. Sunlight penetration decreases super rapidly as we fall, and because photosynthesis is physically impossible down here, absolutely no plants can grow. That means to survive, the creatures of the deep have to rely on some radically different biological strategies just to find a meal, find a mate, and avoid becoming someone else's dinner. Now, the physics of light underwater is absolutely fascinating. Sunlight is made up of all the colors of the visible spectrum, right? But underwater, low-energy red light waves get filtered out almost immediately. Blue and violet light waves pack more energy, so they travel the deepest. And this is a huge deal for survival. Because red light vanishes so quickly, if you are a deep-sea creature colored red, you actually appear completely black. It is the ultimate deep-sea cloaking device. Section 4. Secrets of living light. But here's the thing. Just because the sun can't reach these depths doesn't mean there's no light. Life has actually found a way to build its own flashlight in the dark. It's called bioluminescence. Formally, this is the production of visible light by a living organism through an enzymatic chemical reaction. It's chemistry, not magic, but let me tell you, seeing it in action feels like pure science fiction. And prepare to have your mind blown by this number. You might think glowing animals are some super rare anomaly, but researchers estimate that over 75% of the animals living in the water column of the open ocean produce their own light. Over 3/4. It is not the exception down there. It is the rule. The actual mechanics of this biological engine are so cool.
First, you have a substrate molecule called luciferin, and it bonds with oxygen. Then, an enzyme called luciferase steps in to catalyze and supercharge that reaction. The result of that bonding? A release of energy in the form of visible light, plus a byproduct called oxyluciferin. And the absolute best part is that the luciferase enzyme gets recycled. As long as the animal has oxygen and luciferin, it can just keep firing that chemical engine over and over to make light.
So why even expend the precious energy to glow? Well, bioluminescence is basically the ultimate deep-sea multi-tool. Organisms use it to locate food, acting like a built-in spotlight. They use it to defend against predators, or, amazingly, to hide from them using specialized counter-illumination camouflage. They also use incredibly specific light patterns to attract mates, or just to communicate with their own species across the total void. Take the Atolla jellyfish, for example. It uses its bioluminescence as a literal burglar alarm. Imagine this jellyfish is being attacked by a predator in pitch darkness. Suddenly, it flashes this incredibly bright, vibrant light. Why? It's screaming for attention. It's trying to attract an even larger predator that will hopefully swoop in and eat whatever is currently attacking the jellyfish. It's such a brilliant, chaotic strategy for survival.
And then you have the melanostomias dragonfish. Seeing it under normal white light versus its bioluminescent state is like looking at two different animals. It has these parallel rows of glowing blue light-producing organs called photophores running right down its body. Plus, it has this glowing barbel dangling right under its chin. It uses that glowing chin lure to draw prey directly into its massive, terrifying jaws.
Of course, we literally cannot talk about the deep sea without mentioning the iconic anglerfish. This animal is the perfect synthesis of biological engineering. Floating out there in the pitch-black midnight zone, it uses a highly specialized dorsal fin spine as a glowing fishing rod. In a world completely starved of resources, the anglerfish doesn't waste energy chasing its food. It just waits for curious prey to swim straight toward the light.
Section 5. The Deep Sea Gold Rush.
Now, as much as we love marveling at these alien ecosystems, human engineering is currently returning to the abyss for a very different reason. Our deep-water expeditions have mapped out more than just glowing jellyfish. We've discovered abundant, highly valuable mineral resources scattered all across the ocean floor. Driven by a massive global demand for metals, the International Seabed Authority has already issued 18 exploration contracts in places like the Pacific Ocean's Clarion-Clipperton Fracture Zone. Private companies and researchers are out there actively mapping hundreds of thousands of square kilometers of the seabed, exploring the potential of extracting these polymetallic nodules. Which leaves us with a really profound question to ponder. As we engineer incredibly advanced new ways to harvest the deep sea's resources, how will we manage to protect these fragile, glowing ecosystems that we have barely even begun to understand? It's going to be a delicate balancing act between human industry and the preservation of Earth's absolute final frontier. Thank you so much for joining me on this descent into the dark. Keep learning, keep asking big questions, and I'll catch you on the next explainer.